general relativity step by step. I was talking about transforming covariant and contravariant vectors by the Lorentz transforms, and now I'm going to introduce the general notion of a 4-vector. Well, we know about displacement already. If I talk about displacement, oops, didn't know that could happen. Let's try that again. Displacement, not sure what happened there. We've got t, x, y and z, and we know how that transforms under a Lorentz transformation. If I put the bars over there, and that equals some big matrix which I'll draw in, times t, x, y and z. Let me do the t bar and the x bar. That's just the familiar old gamma, gamma, beta and gamma, and then we just pad it with zeros because we're moving in the x direction. And of course this bit down here is a identity matrix down there. So there we are, we've got displacement, we've got that. Well, that's the displacement. If we start talking about the derivative of displacement with respect to time, we've suddenly got a problem, because whose time do we take it with? We've got a t bar here. We could have, if we call that s for displacement, we might have even full derivatives, ds by dt. Well, that's not really defined, because there's no way to choose ds by dt over dt. There's no way to choose t as opposed to t bar. So that's no good. That's terrible. That's no good. We're going to have to start thinking a little bit more relativistically here. What we actually mean is this: we're setting up a coordinate system where we've got x and t, and we've got a world line. I'll try and be a little bit consistent in my colours here. I've got a world line of some object here which is cruising along like that, and it's got its little light cone here, like that. And we've got E1, and then there might be an event E2 there. Now, all observers agree on the displacement between E1 and E2. All observers agree on that. So I'll call it a delta. So that's a delta s squared, which is delta t squared minus delta x squared, and possibly other spatial terms as well if I had a y and a z term. And so of course we may as well say that delta tau equals the square root of dt squared minus delta x squared. Now, in a coordinate system, in a coord system in which our little object here, our green thing, object is at rest, delta tau equals the square root of delta t squared. I guess, yeah, equals just delta t, where t is time as measured by this person here. So that time there is the time coordinate as used by somebody who's at rest with respect to this particular world line at this particular point here. I know I've drawn it with a little curve here, but that's the second order effect. So delta tau equals the local, not local, you call it the proper time. The proper time along the green world line. And if you define it like this, if you say that delta tau squared equals delta t squared minus delta x squared, because of the invariance of the interval, that's the same delta t bar squared minus delta x bar squared. That's the same for all observers. So all observers agree about what delta tau is. The books make heavy weather of this, that all observers agree on delta tau, but it doesn't matter. It doesn't matter that they can agree or disagree. It doesn't matter. These different observers don't need to agree on anything. They might not agree on what day of the week it is. Delta tau is the proper time, which is the time as measured by somebody who's at rest on this particular world line here. And that's why you call it proper time, because it's proper for him. Proper time, sometimes you see it called wristwatch time. Wristwatch time. Okay, and that's a nice invariant. That's a nice physical invariant. So, when we look at our displacement here, it makes sense to start considering how that displacement changes with respect to proper time. So let's just have a look at that. We've got our displacement t, displacement s here. So I'm going to define for velocity. This thing here is our for displacement, I guess. For displacement. But I'm going to define the for velocity u. Oops. For velocity u. I'm going to try and be consistent here. U I'm going to try and write as capital, for velocities or for vectors in general, I'm going to write as uppercase letters with a sort of swung dash underneath them. Equals ds, which is the for displacement, with respect to dtor. I can't say that it's equal to ds by dt because it could be time as measured by any different observer. Different observers would disagree about what this coordinate here is. So that's the one I'm going to use, and I'm not going to use that. And that's called a for velocity. Okay, so that's the definition of for velocity. And of course, what I'm going to do is to try and evaluate this for velocity here, which is a sensible thing to want to calculate. I'm going to calculate it for the very simplest thing I can think of, which is an object at rest. So it's got a vertical world line like that. It's just at rest. So what am I trying to say here? I'm trying to say that u is d by dtor of s, which equals d by dtor of s, which is just t. Let's just say, well, no, let's just say it's constant. How do I write constant down? Cx, cy, and cz. These are just constants, constant, yeah? Equals d by dtor of t x, y, z. So I'm just going to write tor instead, and that's cx, cy, cz equals 1, 0, 0, 0. So that is the for velocity of an object at rest. For velocity of an object at rest equals 1, 0, 0, 0. There it is. For velocity of an object at rest is just that. Because it's kind of cruising along here, moving in the time direction, and it's just, you say moving in the time direction, it's not terribly sensible use of English, but there's no good way to express this. It's just moving forward in time, because the little person, there he is, he's got a little wristwatch on, which is counting off the seconds, and there they are. There you go, for velocity of an object at rest. Not the most interesting example, I grant you, but that is the for velocity of an object at rest. And what I'm going to do now is to transform it to another frame, and then things will be a bit more sensible. Okay, stop.